Other analysis techniques, Chapter 9, Part 2. Having gone through the meaning of future worth and performing calculations in Excel spreadsheets on future worth and benefit cost ratios, after going through this presentation, students would be able to perform calculations in engineering economics problems using the concepts of payback period and sensitivity analysis. We'll use spreadsheet to carry out most of these analysis. Payback period, the period in which a project's initial cash flow is recouped or equalized by its net revenues. So here are 4 projects, A, B, C, and D, each with different kinds of initial cost and different kinds of cash inflows. A has a decreasing cash inflow schedule, B has increasing cash inflow schedule, C has a constant cash flow schedule, and D has a marginally increasing cash flow schedule. So we find out the payback period using a formula. Let's see the formula. Here we go. We've been working here, alt V, Z0. And so what we use is a formula like this. If function within if and sum of I4 through I5. So I4, the 4 is fixed, and if its sum till now is greater than 0 and M4 is a no, and if the previous cell is a no, then we say yes. Else, if it is still greater than 0 and it was not a no, that means it was a yes, then it will not say no, it's just going to say nope, else no. So what happens is this is actually going to say keep saying no until the sum is less than the initial value. As soon as it becomes greater than the initial value, it's going to say yes. But if its previous cell was saying a yes, then it's not going to say a no, it's going to say a nope. And that differentiates it, because then it's going to keep saying yes because the sum is more than the initial value. And so this continues across all of these. And so where we see the yes is the first time we see the payback period has been obtained. So for example, let's check this. Here you can see the sum is 9,900, and as soon as we move into this period it exceeds 10,000. Likewise here, this is the first time we exceed 12,500, 12,600, and so on and so forth. Now we can go a step further. We can actually find out exactly what part of the payment was used partially. So first thing was to find out the sum until the previous period, and so we realize that there's only a difference of $100 till the previous period. So what part of $1,800, the next period, is the $100? It's about 0.06. So we add that 0.06 to the previous period value, the 5 years, to get a payback period of 5.06. So we can always find out a partial time in which the entire initial money is recouped by the cash inflows, and therefore this is called the payback period rule. Notice there's no discounting of cash flows, there is no present worth, etc. So really it treats $2,000 after 1 year the same as $10,000 at time t equals 0, and that's one big drawback of the payback period rule. But it's still a very attractive way to find out very quickly which cash flow stream gives the money's worth quickly. Now payback period does not necessarily mean the present worth is the same. So for example, we have these 2 cash flow streams in which the initial cash outflow is 50,000 and it has only 4 cash flow streams of 12,500. So initial investment is made up in 4 periods, but after 4 periods is nothing. And for cash stream B, it is 35,000, but it only makes up for 28,000 in the first 4 periods. So the payback period for A is 4 years, but for B is more than 4 years. And how does that translate? Well, the NPV of A is negative, the IRR is 0, and the payback period is nice, it's just 4 years. But the second project, the NPV is positive, the IRR is good, but the payback period is sadly not as good. So payback period has its own drawbacks. Now this example has been adopted from chapter 5 part 1 example 2. If you recall, we were doing a road construction. So this is a concrete road and this is the less less durable method of construction of the road. So we have two cash flows. First is at time t equals 0, and then time t equals 25. We had pretty much set this cash flows in stone before we found out the present worth and the IRR. Now we even find out the EUAC of that using that method. Now let's just make this variable. So what if we say that the $300,000 is flexible? We can invest it at time t equals n, and we actually can now do a what if analysis. And so we can use, let's go back into Excel and do this. So is it this? Nope, it is this right here. Alt V Z 0 enter. It's too large. Alt V Z Alt E Alt C 150 enter. Yeah, that's a little better. So at least we know what we're doing. So how do you find out the PV of method A? Well, what we do is we find out the P present value using a rate. The rate cell is fixed, so $0.7, $0.7, comma, the number of periods is $0.6, $0.6. That's the number of periods. The payment is well, 0. The future value, what are we doing here? Yes, the future value. So this is the actually the number of period would be t equals 0, comma, the payment is 0. The future value is going to be negative of that 300,000, and we will fix that. So negative $0.5, comma, end of the period. So this is the present value of the 300,000. Now we have to add this to the present value. No, so it's going to give me a positive number. So I need to make minus of the minus, which is plus. Nope, that didn't work. The present value of the future value, which is negative, is a positive number, and so the present value of future value $0.5 minus 3, oh, minus of minus, yeah, so present value is negative and plus another negative, so that's a total negative. Correct. Now what's happening here is that as we move Control D, move this formula down, it's going to keep the n and the rate the same. I mean, not the n, the money to be discounted and the rate of discounting is the same, but it's going to change the time at which we install the second project. So that's the present value, and that's why, as you can see, as we move this further and further, now what's going on? Oh, $0.5, not $0.5, it's $0.4. So we didn't fix that cell. $0.4, there we go, and keep going like that. So you can see that's what's happening. It's becoming less and less negative. So this is the blue line, PV of method A. It's becoming less and less negative. The point of importance for us is this point here, and so we can easily find out the value of that point. So instead of what we need is a value of n. Instead of making it R4, let's make it V4. Okay, so let's put a value of 6 here. And so this changed the value of the present value. What we need to do is set this present value equal to minus 350,000 by changing the cell 6. And we can see they meet at 14.2 years. The other interesting thing is, when does this become 0? Alt AWG to 0 by changing this. And so, no. Too bad. It takes time to become 0. It takes its own sweet time becoming 0, and the reason for that is this minus 200,000. It'll taper off at that 200,000 at its extreme point. So even if we make it, let's say, 200 years or 2,000 years, it's going to taper off at that 200,000 negative. So 20 years, 300,000, 40 years, 240,000, 60 years, 216,000, 80 years, 206,000, 100 years, 202,000. So it's asymptotically tapering off to 200,000. That's what we learn from here. So it'll never become 0. All right. So that is this example. Now, what we learned here was a great sensitive analysis in which we could find out the threshold beyond which one method becomes better than the other. So if we install the second road beyond the 14.20 years, then method A actually has a lesser negative value than method B. And we actually found this answer 288,590 when we were solving for that chapter 5 part 1 example 2. Moving on, so we found the crossover rate 14.21 years, and this is the scenario analysis, the graph of one with the other. Now let's look at example 8. Remember this cash flow stream which we just described a few minutes ago? I dropped the D, I believe. Now we can do a scenario analysis here as well. So let's go back to Excel and see what we did. So the scenario analysis for Alt VZ0, enter. Isn't that this? Nope. NPV A, B, and C. We did not. Where did I pick this up from? Oops. This is a different project. Let's just do it. So let's just put the numbers here, and this might take a little bit of time for that. That's okay. Time A, B, and C. Alright, so 0 equals this plus 1. Copy that. How many years? 10 years. Control G, and we'll go to K 13. Control V. One more year please. 10. Alright, so minus 10,000, and the first cash flow is 2,000. It remains at 2,000 for 4 years. Control D, Control D, Control D. Actually, we'll make it equal to that. Control D, Control D. And then it loses steam by $100. So equals that minus 100. Control D, 17, 16, 15, 14. Is that right? So yep, it is correct. And then minus 12,500. And then 800. Is it growing by 150? Okay, so it's growing by 150. Control D, Control D, Control D. Oops. Oh, Control D, 1550. Yep, looking good. Keep going. 2150 is the last one. All right. C, minus 5,000, and single cash flow of a single amount of 850. So that's good. So we can do this really quickly. Control C, Control. Oh, excuse me. Shift Control up. Control V, and then this is done. Now, what are we doing here? So we found out. Let's assume the interest rate. Hurdle rate of 5%. Okay, Control R, Control R. Oops. And then we need to find out the present value. Present worth. So equals, we have cash flow. So NPV rate, comma, the values. What are we doing here? The values plus the initial cash flow. Shift Control 1, Alt O, CW, enter, Control Y. Control R, Control C's R. So 40, 41, 1574, and 1563.47. Alright, and so we will do the scenario analysis. Now, here is the initial cost for B. This is a scenario analysis for B. Scenario analysis for B. Initial cost versus NPV B5 at 5%. And then NPV, well, wait a minute. I know how to do this. NPV first A, and we'll swap it. NPV B5, and then NPV, or we can keep it there as well, no problem. $1,000, right? And then increase it by 1,000. So initial cost is increasing till how much? 14,000. Okay. 14,000. Oh, we went too far. 15,000 is not needed. All right. So NPVA does not change. It's just a single number. Equals that. Fix it. Oh, $sign. Just $16. $16. Yeah, we can do that. No problem. Fixed it. NPVC. Control C, Control V. Looks good. Yep. Control V. Alright, now here's the fun part. Equals NPV, the rate. Let's take the rate and fix that rate. Oh, $15. Okay, comma, the values. The values are all these. Fix them. So $5 $5 colon $14. Excuse me. $14 comma. Now, what is the initial value? The initial cost is going to be minus of this. And this will change as we move down. So 10,340. Why did it not match? Well, we will make sure you're not making a mistake here. So NPV, the rate's 5%. The range is M5 through M14 and minus P4. Let's keep moving. Let's see if it matches at $12,000. 3, 2, no, there's something wrong, definitely. So M15, the rate, M$5 through M$14, that's correct. These are the values. Why did we take the minus P$4 inside? It has to be outside. Minus P4. There we go. That's more like it. 9925 matches. Happens when you're doing it impromptu, doesn't it? Just a matter of parentheses. All right. And so when we plot this, we see that exactly is what we need. So put that there. Now the points of interest for us essentially are 3. So I'm going to take that and paste it here 3 times. 3 points of interest. First point of interest is where the difference between B and A is 0. And the second point of interest is where the difference between B and C is 0. And the third point of interest is where the difference where B itself is 0. So first let's do that. Alt A W G. Well, 0. What initial value? Cell must contain. Oh yeah, right. Copy that, paste it. Sure. Alt A W G, 2 value 0 by changing this. So 10,925. At 10,925, this will go to 0. That is the initial cost. So that makes the IRR equals 5%. The second is when does C and B have the same NPV? Alt AWG to 0 by changing the 2000. So 9361. Let's go to the graph. Yes, 9361 is when B and C meet in NPV, when the initial cost of B is 9361. And then finally A and B, Alt AWG to 0 by changing 1000. So 6883, that's a 6883. When it's 6883, the NPV of B and A are the same. And that's exactly what we see in the next slide. So we are interested in this point, 6883, 9360, and whatever that number was, 10,925. So these are 3 key numbers of NPV. So scenario analysis is really beautiful. We can find out anything under the sun that we like, particularly using the power of goal-seek in Excel. So using a series of goal-seek analysis just does the job for us. It's amazing. We will do one more scenario analysis. Now this is chapter 5, part 2, example 1. We had 3 P's, P1, P2, P3, I believe in that example, 3 products. Fixed cost was 9,000. Net revenue is $1.51 per unit, little modified. 1,700 units per year. Net revenue is 25. So let's just go back to the example. Let me save this. I don't want to miss it again. We skipped that one. All right. So let's see. So this is the net revenue. Net revenue is just nothing but the revenue times the number of units. And so the rate of discount is 4%. The present value of the benefits is nothing but the PV function applied on the net revenue. So we're converting an annuity into a single present value. And the present value of cost is the fixed cost. That's it. And the present worth is a difference of present benefit and present cost. And then the B to C ratio is 1.27. All right. Now, sensitivity analysis basically tells us what if the cost increased by 5%. So you can see the initial cost went up to 1.05 times that in the first scenario. Everything else is the same. Notice how we fixed J, J4, $J, $J, etc. And so this is just a product of the two fixed cells, so it's going to be fixed itself, $J, $J. And so we just copy the formula down and take the difference and take the BC analysis. But the idea is this. So when the cost goes up, the BC analysis shows a lower number, which means the costs have gone up and the present value has gone up. Now, net revenue down by 10%, BC will show us a lower number. So the benefits have gone down. Production down by 15%. Again, B will go down. Now it's 1.08. It's getting close to 1. It's getting less and less profitable. Life down by 1 year. By the way, these are only increments from here, from P1, okay? Everything else is constant. So when we are changing the production by 15%, we're only changing the production by 15%. So 1445 is 85% of 1700. Everything else is what was here in this particular column. Okay, life less than 1 year, decreased by 1 year, then the BC analysis shows that less benefits. So the present value of benefits has gone down. Please note, present value of benefits goes down when the life of the machine is a year lower. Other important thing to note, when a discount rate drops, the present value of benefits increases. The present value of cost does not change because when the cost is initial, and therefore BC ratio goes up. So when interest rates drop, BC ratio increases, all else constant. And likewise, when interest rate goes up, BC ratio drops from 1.27 to 1.25 because now the benefits have become, the present value of benefits has gone down. So that is how we do scenario analysis. And what we've studied is the effect of increase in cost, decrease in revenue, increase in the or decrease in production of units, change in the life, and change in the discount rate. That is scenario analysis. To summarize, the future value and BC analysis provide more alternatives in economic cost analysis. We've looked at the payback period in this presentation. We've looked at payback period is speedy but simple. It's too simple, unfortunately. Payback period is approximate, not exact. The different timing of cash flows are not respected by this method, and all economic consequences are beyond the payback period are ignored. Calculation is not accurate. It's approximate, just like because it ignores the economic impacts of present value and discounting. Sensitivity and break-even and what-if analysis are extremely powerful methods of presenting management information systems, which are very, very useful for engineering economic designs. So we used to see how decisions can change with a small change in different parameters. That's the power of Excel. And that's Chapter 9, Part 2. Thank you for listening.